Alright, now here's a treat. This is the Quantum Mechanics Solver. This is a really interesting book by Basdevant and Dalibard. I came across the first edition of this book. This is the second edition from Springer. When I was in graduate school, and and I wanted it so much that I picked this up later on. We'll talk about that a little bit later on, but I want to talk a little bit about what makes this different. All right, so this book is really just problems. Okay, this is a book of problems for you to learn quantum mechanics, and it's set up in a very coherent way, so that you basically have one sort of problem that you're working on over a chapter. Basically, you have one problem over a chapter, and you're exploring the problem, and it's a very good way to learn this. These guys do have a regular textbook on quantum mechanics that I've never quite gotten myself to pick up because I've got a lot of textbooks on quantum mechanics. But I found this a very good thing once, and I think it's something that you might want to pick up if you really do want to understand quantum mechanics, because I think that the regular theory is very important to understand, and I think you can take some very good popular presentations of quantum mechanics, and you can get a pretty good idea about what's going on. But you never really understand something until you use it. And the more involved that use is, the better you understand what it is you're trying to do. And that's true for quantum mechanics, that's true for electromagnetism. I didn't really understand electromagnetism until I actually had to use it to build things, right? And that's going to be true for everything in physics, is that at some point, the rubber hits the road, and that point is, well, either you're going to design an experiment or you're going to do some calculations. And that's how you're going to figure out if you actually understood things, right? I mean, and that's the reason why doing problems is the best way to learn to do things. You can see here that the summary of quantum mechanics here is like 15 pages long or something like that. So that's basically all of a semester-long quantum mechanics course right there. That's true for most classes. It takes a semester to build up, to work up through all this stuff, but in general, what you really need is to focus on these problems. There's not a lot, right? Let's say Physics 1, your standard Newtonian mechanics class. There are maybe 7 forces that you have to learn, maybe less. There are, Newton's laws and conservation laws, and some rotational analogs. There are really only 20 things in the entire class, but you keep doing them from different angles, and you do them in different ways, and you're just hoping that the intuition will start to click when you start mixing things together. And that's sort of always going to be true for these classes. Once you understand something, you can condense it down into a very brief summary. Now, when I picked this book up, the second edition, I had to actually go and find the first edition. And that's because in the first edition, rather than starting with neutrino oscillations, I don't think they had neutrino oscillations in there at all. They started with color centers in crystals. Why do crystals have different colors? And actually, what I wanted to do, why I picked this up, was I wanted to try to see if I could fit that into my modern physics class. First, you have to redo it and learn it again to see if you can. But I thought that would be an interesting example for talking about quantum mechanics. But when I got this, it starts with neutrino oscillations instead. Again, I think I left the other book at work, so I can't check right now, but I think that was another problem. But neutrino oscillations are incredibly interesting, and they're actually incredibly weird. So you're starting out with something really, really topical, something really new. And that's one of the things that's good about this book, is if you're using this as a supplement to a regular quantum mechanics textbook, possibly theirs, then what you're doing is you're making sure that your students are getting an idea about what's going on in the real world as far as this physics research is going. So this is basically the quantum mechanics of neutrino oscillations. Then moves on to the next problem, which is basically atomic clocks, and you see that's about 8 pages. This was about 12 pages. Then it talks about neutrino interferometry. So you're talking about interferometry, that's important. Gravitational effect, that's interesting. It's been a while since I've looked at it. Let's see, does this have what I think he's talking about? If so, it's awesome. And yes, I think it is. Yeah, the gravitational field being, or I guess you have to be potential in quantum mechanics. So, I mean, gravity really does work in quantum mechanical terms. So, I mean, you know, just because there's no unification doesn't mean you can't use quantum mechanics and gravity in the same spot, just as long as, you know, it's not too small, and it's not too fast, and it's not too massive, and all that other stuff. Quantum mechanics and gravity, they work fine. Actually, probably if it's going just really fast, you can still use it. Let's see. Spectroscopy, that's not there. The analysis of the Stern-Gerlach experiment, that's very important. I mean, I think I did a video on that. That's a really, really good way to learn about what's going on in quantum mechanics. Measuring the electron magnetic moment anomaly. Okay, so that's just the magnetic moment. That's really, really good. That's something we have to learn about is that. I think I'm going to say that's G-2. The decay of tritium, spectrum of positronium, that's the spectrum of a positron and an electron in an orbital state, in the sort of pseudo-atom. Hydrogen atom and cross fields, energy loss of ions and matter, very nice. Quantum entanglement and measurement is part 2, and here you go. Well, actually, I mean, these are all atomic. These are all very, very topical. There are things in here that you really need to know that are basic and that are bases of a lot of other experiments. Here we go into things that people still like to argue about. So these are the good things, right? So here you're going to spend almost 20 pages on the EPR paradox and Bell's inequalities. These are very important, right? These are very important to understand, and to really understand what the problem is with Bell's inequalities, you have to be able to calculate it, right? You have to be able to calculate, and that means not that you listen to podcasts, right? Not that you read Brian Greene books. They're not novels. Not that you even read a textbook, right? It means that you've gone in there and you've struggled with making the stuff work out, struggled to figure out what's going on, the differences between these two kinds of ways to calculate the probabilities. Schrodinger's cat, very important in the measurement problem, right? So what does that mean? Why do we do that? You want to get in there and use it. Quantum cryptography, very good, especially nowadays, right? Now we're getting to the point where we've got the quantum computing, quantum cryptography is an important part of that. Some more stuff that goes directly to experiments, like this gravitational stuff we did previously. The direct observation of field quantization, ideal measurements. This is a von Neumann thing. Yeah, von Neumann. There we go. Very important. Going through the measurement process to make sense of things like Schrodinger's cat, right? And maybe not so much the EPR problem, but the EPR problem is also very important for that. Quantum eraser. That's a weird one. That's a good one to do. And a quantum thermometer, which I probably didn't work because I don't remember anything about it. And then come to part 3, which is more complex systems. That's almost the last part. Yeah, okay. A three-body problem, exact results for the three-body problem. Isn't that fun? For, certain things. Oh, you get into the quark model there. Bose-Einstein condensate. That was still pretty new. Well, not new as in thing, but that was still only recently discovered when this second edition came, or not discovered, verified, excuse me, when this came out, the first time somebody saw it. I remember that distinctly. I was surprised that it showed up on the physics GRE when I took it. Let's see, magnetic excitons. So we're getting into some real condensed matter stuff when we're talking about excitons. Quantum box and colored molecular ions. I may have been wrong. No, this is different from the color centers, but still, this might have been something I could have used. Hyperfine structure in electron spin resonance. All right, ESR, very important to me because that's basically what I used in graduate school and for 10 years after that. Probing matter with positive muons. That sounds pretty fun. Quantum reflections of atoms from a surface. Laser cooling and trapping. Oh, this stuff is so cool, right? I mean, really working through the statistics of that and how that actually works is a lot of fun. And block oscillations, if you're doing anything, right, you need to know about that. So you've got all of these things. You've got 27 different problems, each 10 to 20 pages long. And you know, they're broken up into different parts. So let's take a peek. So this is just, you know, all of sort of the theory, the bare bones theory, right, which sort of gives you all sorts of things. Do we have the cross section over there, Born approximation there? That's what I was looking for. That's what I was thinking of. So got all those things that, you know, you spent a week on in college doing stuff like that. So let's grab a random one out here. Let's see. Oh, yeah, let's look at the quantum cryptography. So you see how each one of these chapters is set up is, you know, there's a short introduction, a tiny little bit of theory, and then you're supposed to go through and basically using quantum mechanics and the correct sort of kinds of quantum mechanics, solve several problems. So there are 4 here in 13.1, 4 problems, and that's sort of to give you an idea about how the system's working. And now you're going to 13.2 and you're doing some more work, another 4 or 5 problems. How many? Another 4. And you see again, you've got a few. I hope that didn't pause because the computer went to sleep. Let's see, we've got, so as I was saying, we've got these got these illustrations sort of showing you what he's talking about between source and detector angles and stuff like that. Let's see. Alright, so this is an interesting little table here, you know, trying to describe these different things about how the procedure goes. So that's the sort of thing you get a lot in a lot of these descriptions about entanglement, is a little procedure that looks like that. So that's something in there to look at. Then we have another section. So we've gone from, you know, the basic idea about the system to a little more advanced ideas about the system, including getting used to the procedure idea. Then we go into the quantum cryptography procedure. Let's see how many problems do they have. See, this has almost no additional work in there. And that one has 5. And then after that, there are a couple of pages of solutions. You see that the solutions are really small, right? They're not detailed. So this is something that you should be able to do is you should be able to write out like a solution, right? Why are you doing what you do in your solution, and stuff like that. This is more or less the way you should talk about solutions. Nobody should give a student solutions that says, here's the equation, plug in the numbers, right? The explanation should be in there saying, okay, you want to try to do this in order to do that, and blah 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 blah. This is, these are the things that are going on. You should be using this sort of, and because of that, you should have this sort of procedure and stuff like that. And even with the solutions, the student has to do the work, all right? Because that's the only way to get any understanding in there. So that's what those look like. So again, I like these. I like this book. Unfortunately, this isn't the one I actually worked through. I worked through the other one because I had to go buy it. But this was the one I had at home, and so I pulled this out today. It's a little nicer looking than the earlier version, but the earlier version has that sort of classic feel. It's one of these. It has a cover like this one instead. Okay, so that is the quantum mechanics solver. Again, a very good, interesting book. This is a good way to learn things. Maybe after you go through with Townsend or something like that, you could go through this over a summer or something like that, and really beef up on your quantum mechanics. Say before you go to grad school or something. I think that would be a pretty useful thing there for you to do. All right. So, thank you very much. I'll talk to you next week. Bye now.